if we're looking at a hyperbola, last class I kind of discussed with the cones what you would do to chop a cone and make a hyperbola. But just to kind of show you that this shape exists in real life, I'm going to go move my mouse in a second because it's right in front. Do you see this lamp?
Yeah.
You see how if you look at the top lighting of the lamp and the bottom lighting of a lamp, it creates this like U and an upside down U sort of situation? That shape is called a hyperbola. So these are shapes that you would see in actual real life, kind of like an ellipse. If you ever work with lighting, you will have to understand how light is thrown across rooms, which includes potentially a hyperbola. Okay? So yes?
So this is only used for like light?
No, not only used. That's just an example of where it is. But this shape, boom and boom, is the hyperbola. The two parts of it are officially called branches, but I just call them pieces myself. But if you're talking about the top branch and the bottom branch, that would be the correct terminology to use there. Let's talk about the different pieces of a hyperbola. The hyperbola is the set of points in a plane, the difference of whose distances from two fixed points called the foci is constant. If we remember the ellipse, it was the sum of the distances. A hyperbola is the difference of the distances. But we have a lot of the same vocabulary. So we have the foci. What do you notice about where the focuses, the foci, are for this hyperbola?
They're outside.
They're outside. They're like in the bowls themselves. So they should be surrounded by the bowls or the branches. The line through which the foci intersects the hyperbola at 2 points, those points are called the vertices, so that has not changed. It is still like part of the shape itself, like it was for an ellipse. The line segment that joins the vertexes is no longer called the major axis. It is called the transverse axis. So it is what connects the two vertices together. Notice that the transverse axis is not inside the shapes, not inside the branches. It's in between the branches. That's the transverse axis. The midpoint of the transverse axis will be the center of your hyperbola. So we do still have a center of the shape, but notice the center is in between the branches this time instead of in the center of the ellipse like it was before. Notice that the center lies midway between the vertices as well as midway between the foci. So that is still the same as it was for the ellipse. The center is truly in the center of the foci, the vertices, and the shape itself. Now let's look at the formulas for the hyperbola. There are two options, just like there were two options for an ellipse. What do you notice that initially is different in this equation from the ellipse equation?
Minus.
It's minus. So we will have to recognize now the difference between when I'm presenting you with an equation for an ellipse and an equation for a hyperbola. But that's the easiest thing to do. Ellipse is the sum, so they put them together. Hyperbola is the difference. Y'all look over here at my hands for a second. Here's how I remember this. The ellipse is the sum, like I'm putting my two hands together, so it makes an ellipse. And the hyperbola is the difference, like I'm splitting them apart. So if that's helpful for you to remember the ellipse and the hyperbola with the sum or the difference, that's how the formula might be helpful. What else do you notice about the difference between these two equations printed on your paper?
The bottom one is the top one, like the top. The X and Y are flipped.
Great, X and Y are flipped. Do we remember what was flipped in the last one?
A and B.
Did the A and B change in this one?
No.
No. So in this one, for us to have a transverse axis on the x-axis, which means that our shape would look like this, the branches would be side to side, we should have an x value coming first. Transverse axis is the x-axis. For us to have a transverse axis that is on the y-axis, the y's will come first. And that means that we're going to have branches or bowls that go up and down instead of side to side. Do we see the difference in those formulas? Notice that notice that A this time is necessarily always first. The X and the Y are going to change for this one. Now to kind of, again, see the differences in the letters we will use, where did the A and the B come from? Great question. If you have the vertices that are A units from the center, they are literally going to be that distance from the center of the hyperbola. So if here's the center, right? We know the center. A distance away, either above or below, whatever your center is. The foci are still C units from the center. That's still nice because that was the same in the ellipse and the hyperbola. The foci are C distances away from the center, above or below. The formula to find C is a little bit different. This formula is exactly Pythagorean theorem. So if we were going to solve for C given the equation, it would be C equal to the square root of A squared plus B squared. What was the formula last class? Minus B squared. So the ellipse is minus, the hyperbola is plus when we're trying to find the C value, the foci. Let's just add a few more color things here to our graphs, just because it'll be nice. We have our transverse axis, just to make sure we see where that is. And then we're good. There's no minor axis here yet. Dun, dun, dun. Okay, we're not going to graph them just yet because we actually need a few more pieces of information to be able to accurately graph a hyperbola. But let's just make sure we understand the formula themselves. So on the back page, we're going to find the vertices and locate the foci for each of the following hyperbolas with a given equation. Okay, first things first. Is this hyperbola going to have a transverse axis that is side to side or up and down? Side to side. How did we know that? The x comes first. And in this case, it's always the a will be underneath the first term. So here's what I know. I know that this formula is really x squared over 4 squared minus y squared over, not 9 squared, 3 squared. Fabulous. So that means for me that the a value is what? 4. And the b value is what? 3. So if I was finding c, I would use Pythagorean theorem. A squared plus b squared, which I guess I could just go back and actually make these the squared numbers, which is 16 plus 9. Well, 16 plus 9 is 25. What's the square root of 25? 5. Awesome. So here we go. Let's actually answer the question here. It wanted us to find the vertices. The vertices are always going to be a distance away from the center. This one is centered at the origin, because we don't have any numbers added, subtracted to x or y, which means we're going to go an a distance away on the x coordinate because we have an x transverse axis. So this would be -4, 0 and 4, 0 for my vertices. Those of you who have already started your homework, you already saw how these questions are being asked, and it's very similar to this. For the foci, we're doing the same thing, and since they are still on the same transverse axis plane, not necessarily on the transverse axis, but in the same direction, for the foci, we're going to add and subtract the C number to create the locations of the foci for this hyperbola. Does that feel okay for everybody? Okay, somewhat. It feels exactly like we did for the ellipse. It's just a different type of shape. Yes?
How do we get that?
How did we know where to put the number?
No.
No.
So, like with the square root we did yesterday, how did we do that again?
The last time the formula was a squared minus b squared to find the c value. This one just happens to look like Pythagorean theorem. So the formula, okay, I see your question. So the formula for the ellipse, it was c equal to the square root of a squared minus b squared. For the hyperbola, it's c equal to a squared plus b squared. So there's a different formula to find c when you have a hyperbola and an ellipse. Was that your question? Okay. Fabulous. Now let's see what one might look like on a graph. So here we go. We have the standard form of an equation of a hyperbola. That's what we're trying to find. When it has foci at 0, -3 and 0, 3. That's our foci. And it has vertices at 0, -2 and 0, 2. They also gave us a figure to see what this looks like. That's so nice. Question for you. Is my transverse axis parallel to the x-axis or the y-axis? The y-axis. So that means what letter should come first in my hyperbola equation? Y. Okay, so we know that we have a transverse axis. That means we're filling out the y version. We need to know a few things. What is the center of this hyperbola? 0, 0. Now I'm going to start doing a lot of work for a very little because I think this will help us later. Our center is at 0, 0. Do that in the right color. We know our A value. We know our, oh, that's wrong colors again. Let me ask it actually as a question. Do we know our A value?
Yes.
What is it?
2.
2. How did we know it was 2?
Because it's 2 vertices.
The vertices, they're controlled by the A value. B, we're not going to know quite yet, but we do know the C value. What's the C value?
3.
3, because that helps with the foci. Okay, so now we got to work a little bit backwards. We have A and we have C. We need to find B. If you flip your paper over, the book already solved this equation for B for you. The equation for B, if we flip our paper over and look at it, is B squared equal to C squared minus A squared. Okay, so that means we're going to do 9 minus 4. What is 9 minus 4? 5. So B is the square root of 5. We had to solve for B this time because they didn't give it to us. But now that we have B, we can fill out our standard form of the hyperbola. What letter should go first again? Y. So this is going to be y squared over what number?
4.
4 squared. Oh, sorry, 2, which is 4. I'm going to show my work. 2 squared, which is 4. Then we're going to subtract x squared, and we're going to put that over what? Square root of 5 squared. And that's going to be equal to 1. Amazing. So beep, beep, bop, we get our math going. This is y squared over 4 minus x squared over 5 equal to 1. Now I need to bring our attention to something important that is changed from the rules from an ellipse to hyperbola. In the ellipse, what number was always bigger, A or B?
A.
In this problem, is A actually bigger?
No.
So that rule does not apply. A is always underneath the first term, not necessarily that it's bigger. That's a rule for ellipse, not a rule for hyperbola. Okay, a lot of little detailed rules when it comes to these characters, and here we go. Here's why I haven't had you graph anything just yet.
I see squares.
Because hyperbolas actually have slant asymptotes that help us draw the graph more accurately. So I'm going to highlight my asymptotes today in yellow. They're going to be straight lines, but slanted straight lines called slant asymptotes. Finding the equation of these slant asymptotes is not scary. When we had to do this in previous units, you either needed long or synthetic division. We don't need that. All we need to know is the A and the B value. And guess what we're given in a standard form equation? The A and B value. If you have a hyperbola that has a horizontal transverse axis, so that means that we are looking like this business, then your formula for the asymptotes, I'm going to simplify it down because this is how I'm going to have you write it for me. You're going to do plus or minus B over A times X. B goes first, A goes second. Is that the lunch one or is that the almost lunch one?
That's lunch one.
That's an almost lunch one. Thank you for
Can you put
almost.
in something darker?
Is it too light? Okay, I'll just do it in black. If you have a hyperbola whose transverse axis is vertical, meaning you have the up and down bowls, your formula for the asymptotes becomes plus or minus A over B times X. And again, all of this stuff is very, very similar, so it's going to be important that you really make good notes here into what to use when. I believe on your homework when it asks for the asymptotes, you have to type them separately. So do one of them with a plus, one of them with a minus, but for me, you can combine them into the same. Now, what does this mean? Before we move on, I want you to see what these asymptotes are doing. For the first option, when we had a horizontal transverse axis, okay, the sideways bowls, you see that this square has been created in the center of the hyperbola. That square is going to help us draw our asymptotes really, really well. So after lunch when you come in, you're going to actually pick up a ruler so that we can make really nice straight lines. I won't make you get it now. But if we look at the slope of these really straight lines, this is up B and over A, which is why my slope is B over A. So we would have these diagonal slant asymptotes following the positive and negative version of that slope of B over A to a minor point, that's not really a point, and then your vertices, rise and run. And vice versa, if I have the vertical transverse axis and I still look at that slope, it's still going up. This time it's going up A and over B, which is why that fraction changes. After lunch, we will get a ruler and we will definitely make sure we can graph these things. Great, welcome back from your 30-minute lunch break. Let's try to graph some hyperbolas, yeah?
That was pretty specific, miss.
First thing we're going to do when we're graphing hyperbolas is locate the vertices. Now I'm going to highlight this one in blue because that's the correct color for the vertices. If you remember in the ellipse, we also had these things I made up called minor vertices.
Yeah.
It is a vocabulary word in some textbooks, but it wasn't in ours. I'm going to act like there are minor vertices for this. The words doesn't make sense anymore because it straight up doesn't touch the hyperbola. But if we keep thinking about them as the blue and the purple like we did last time, they came from A and B, same vibe, we will get the points that I want. We're going to use dashed lines to draw the rectangle that is centered at the origin, which will later be centered at our center, with sides parallel to the axes crossing one axis and the other at those points. We're going to use dashed lines to draw the diagonals of this rectangle. Oops, that should be yellow, that should be yellow, that should be yellow. It's not switching to yellow. Switch to yellow, please.
No.
Okay, I got to switch to yellow. I don't know what's happening there. You use dashed lines to draw the diagonals of the rectangle and extend them to create these asymptotes. Once we have the vertices and the asymptotes, we will also plot the foci. It doesn't say to in here, but we also want to include our foci in our drawing. So that's the pink point. And then we're going to draw the two branches of the hyperbola by starting at the vertex and approaching the asymptotes. Follow along with me. Here we go. First things first, we have this equation. We have x squared minus over 25 minus y squared over 16 equal to 1. So question for you, is this going to have a vertical or a horizontal transverse axis? Horizontal. So we know that means that we will have a hyperbola that opens side to side. Just for practice for later, when this is not on the center of our hyperbola is at 0, 0. The A value is what? 5. Remember, A is always first in this one. In the ellipse, that could change, but in a hyperbola, it's always first, which means B is what? 4. So we want to plot out, let's just go ahead and find C. We're in that mode. C is found by doing A squared plus B squared. 25 plus 16 is 41, which you cannot take the square root of. So that is C, square root of 41. Okay, we need to find the vertices. If we know that the A value is 5 and the center is at 0, 0, where are your vertices? If we know our center is at 5 and the A value is 5, what? Our center is at 0, 0, and the A value is 5. Where are our vertices?
Negative 5, 0, 5, 0.
Very good. So they're along the x-axis because this is a horizontal transverse axis, and we have these vertices at negative 5 and 5. I also now want you to plot the purple points above and below the center like we did the purple points for the ellipse. They were minor vertices before. They're not even vertices, but they're minor points. They're going to be 4 above and 4 below the center. You are then going to draw a box. That box is in that information. This is a little dashed box. It's not actually part of the real hyperbola, but it will help us draw it. Do we see how I've created the box with the A and the B value? Okay. Let me go ahead and plot my center point so you can see that that's there. Now, our asymptotes are going to be the rise and the run that gets you from the center point to the corner of this box. If I go from the center to the corner of this box, what is the rise? What's the run? So my asymptotes here are going to be at y equal to plus and minus rise of 4, run of 5. That's what you guys just told me, right? Which means, oh, and I forgot to hand you rulers like I said I would. Be right back. So sorry, now that we have our rulers, let's draw some nice straight lines, but we are going to connect the dots together. So with your ruler, you're going to place your ruler down and try to get it to touch the corner of the box in the center so that you can draw, oh, that should probably be dashed, a dashed line. I am using a ruler. Are you laughing because it's still not straight?
Yeah.
Listen, I'm drawing a ruler on top of an iPad, so it doesn't really work very well. I'm going corner to corner and through the center.
Wait, is you like a line tool on it?
It's also hard to use, I'll be honest. I know.
This.
My millennial is showing, okay, guys?
This.
Corner to corner and through the center. Boom, 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 boom. Yeah, math degree on paper pencil, not on an iPad. Oh, I dropped my ruler. Okay, boom. We have our asymptotes. Now this is, if we're highlighting this with our color scheme, this should be yellow, right?
Should.
There's our asymptotes that create the shape. How are we doing with our rulers?
Really good.
Amazing. Thank you, Genesis. The only thing we need, just to make sure our graph is right, and because I know it's going to ask you about it, is we need our coordinate points for the foci. Now, the foci is going to be side to side of the center because it needs to be along the transverse axis, which means we're making this coordinate point negative square root of 41, 0, and positive square root of 41, 0. And if we're like, whoa, Miss Quigley, how do you plot that point? This is approximately negative 6.4, and this is approximately 6.4. So if I were plotting that point, it would be at those approximate places. Approximately negative 6.4 and positive 6.4, 0.
We can go back.
Yes, I can. I just couldn't get that accurate. Sorry. Because once you have your foci, you have your asymptotes, and you have your vertices, you can do the following. Here comes the actual shape itself. You start at the vertice, you get as close to the asymptote as possible. Start at the vertice, get as close to the asymptote as possible, and repeat on the other branch. The other part, boom, and boom. We double check that our foci have ended up inside the branches themselves, as if it was some sort of like, oh my gosh, I was about to make myself sound really old. You know those satellite dishes? You know how there's like a dot, like a little point inside a satellite dish?
Oh, yeah. Oh.
The foci, in reality, parabolas are used to create satellites, and boom, they have a focus in them, and that's what we're doing. Yes.
You're not that old.
Thank you so much. Gold star.
Cesar, remember this.
Gold star.
You still have a station.
I do not have a satellite dish. We never had satellite because we were not that rich.
Oh wait, isn't it that? Oh wait, I have.
Now you got
Yeah, satellite's not that expensive.
And we're distracted about satellite dishes. We will get there. So that's one of the applications of these shapes, specifically parabolas, which we'll do next time. But the same idea with the focus being inside the bowl, inside the branch. That's why. Here's our other one on this page. What do you see as the immediate problem with this equation?
This, it's like the other ones.
Great. What did we do in the other ones?
We divided 36.
Oh yeah.
Divide everything by 36. Now, this freaked people out the other day, so let me take it piece by piece. I'll show a little bit more work. We know we're going to do 9y squared over 36, and we're going to do 4x squared over 36, and then we're going to do 36 over 36. This is what I did last class, and I realized I lost some people here. When I do 9 over 36, here's the cheat code. Do it backwards. What's 36 divided by 9?
4.
But that belongs in the denominator because 36 was bigger. Here's another cheat code. What is 36 divided by 4? 9. But that needs to go in the denominator because the 36 was in the denominator. 36 over 36 is 1. Okay, fabulous. Based on this formula, and let me go ahead and write it one more where we can see the squared showing. This is going to be y squared over 2 squared minus x squared over 3 squared equal to 1. Is this hyperbola going to have a vertical or a horizontal transverse axis? Vertical. Keep that in mind when we start to graph. First things first, we need the center. Where is the center of this hyperbola? 0, 0. Now that's going to change soon, but it's 0, 0 because there's no number added and subtracted to x and y inside the squares. What is the a value?
2.
Very good. It does not move. It's always first. What is the b value? 3. So what is the c value? We get that by doing the square root of 4 plus 9. 4 plus 9 is 13. Can you do the square root of 13? No, we're going to leave it as square root of 13 for accuracy. Okay. Things I know we need. I know we need to know the equation of the asymptotes, and it's hard to remember the correct formula. So instead of trying to remember a formula, we're going to figure it out.
Okay.
We're going to plot the center. It's at 0, 0.
Yeah.
We're going to plot our major vertices, which are the blue points. You told me that this was 2. Do I count 2 above and below or left and right? Very good. So here's my blue vertices. And then I need my purple points, which are not real points, but they help me make this box. I should go to the left and the right. How many steps? 3. Okay. So then I'm going to make this cute little box. Beep, 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 beep. Cute little box. Okay, if I was going from the center to the corner of this box, what was the slope I would need to use to get there?
2 over 3.
Up 2 over 3. So my asymptotes for this graph are going to be at y equal to plus and minus 2 over 3 times x, because you told me up 2 over 3. That will give me the slope that I need to follow along this graph. But also you have a straight edge, you have a ruler. We can just use that on the box itself to create the asymptotes. So we take our protractor or our straight edge or our ruler and we get it to fit on our screen. And then we draw our asymptotes across the box. This is a lot easier with a pencil than with an Apple Pencil, I will tell you that. And then you go the opposite direction. I need to get a smaller ruler is what I need to do. I'm using a protractor because it's smaller, but my iPad has a case on it, so it's like doesn't fit.
Oh, I thought it was like touch sensitive. I was like,
No, it's a straight up protractor. No, imagine I'm gonna drop it. I've never dropped this thing, but if I take the case off, I will drop it.
Really?
Yeah, that's like the, what is that principle of chaos? Anything that can't go wrong will go wrong.
Oh.
That will totally happen for me.
Darwin said? Not Darwin.
No, not Darwin. What is that guy's name? It doesn't matter. We're off topic. Anyways, Murphy's Law. Thank you. Okay, so the other thing that we need before we finish this problem is the coordinate points of the foci. Now, because this one has a vertical transverse axis, we're not going to add and subtract the number c from the x-coordinate. We're going to add and subtract it from the y-coordinate. So it's at 0, negative square root 13 and 0, positive square root 13. I don't know if I said that right because I was just talking really loud and distracted by the bass so you can hear from outside the classroom right now. Wow. Your eardrums are dead.
No, they're not. Yes.
That person's eardrums are, for sure. Wow. Seriously, that is so loud.
Probably have the windows down.
My gosh.
Can you windows have them like on?
Can y'all see it out the window? So we can plot the foci now at 0, negative 3.605, which is going to be approximately like beep, right? That's not right. Like here and here. Wait, I still didn't put this in the right spot. Here. Yes, I can. Once you have the foci and you have the asymptotes, remember you have to get close to, but you cannot touch these diagonal slant asymptotes. You are going to connect the vertices, the major vertices, that's the blue points that should surround the foci to create your hyperbola. So we will look at something like this and like this. Oof, not my best. And then boom, and then boom. Ta-da!
Not ta-da.
If your asymptotes are really super steep, towards your shape, it will be like more U-y. Or if it's really wide, it will be more flat. It just depends on those asymptotes. Yes. I'm recording it right now.
Oh, you want?
I wasn't here yesterday.
Oh, yeah, you weren't. You missed out.
Last class, when we moved the ellipse off of center, we did really well when we kept a hang on where our major axis was, which means we need to make sure we realize where our transverse axis is. The first formula is going to show you the equation where you have a horizontal transverse axis, which means that the hyperbolas, are opening side to side. Everything kind of translates from ellipses to hyperbolas, meaning your center is at H and K. Those are the same letters we used last time. The vertices are now at the adjusted H and K that take into account the A value. This is what we did on the blue kit before, where we add and subtract the A value from the X coordinate because we have an X transverse axis. The foci also changes with the X coordinate, and the minor vertices change with the Y coordinate.
What?
So if we're drawing our box, when we graph it ourselves, we just have to count, but plotting the coordinate points themselves is a little crazy. Otherwise, if we have a vertical transverse axis, that means that our coordinate point for our center is going to be adjusted to find our vertices, but we're adjusting it by adding and subtracting A to the Y coordinate or to the K coordinate, so that we're moving that point up and down and not side to side along our transverse axis. So we have a horizontal transverse axis, and we have a vertical transverse axis. That's the difference. It works the real same as it did for when we started translating the ellipse around the circle, around the graph. So it really, if we can hang on, we got this.
Hold on.
Oh, sorry. I forget all the capping and uncapping of the lids takes a while. Let's do it. Okay, first things first. Let's look at this equation. This equation is x minus 2 squared over 4 squared, because 16 is 4 squared, minus y minus 3 squared over 3 squared equal to 1. Does this hyperbola have a vertical or horizontal transverse axis?
Horizontal.
Horizontal, which means it's going to open side to side. Okay, let's start at the beginning. What is the center? 2, 3, because next to the x is the h and next to the y is the k. Why did I write a 2? Great question.
There are a lot of 2's in this equation.
There are because of all the squareds. What's the a value? 4. What's the b value?
3.
So what's the c value?
Square root of 12.
Oh, not 12. We're going back to the squared version. So square root of 16 plus 9, which is 25. And the square root of 25. Ooh, this one's going to be nice to plot. We love that for ourselves. Yay! Let's plot all of these things so far so that we can see how this changes when we are going off of the origin. This time our center is at 2, 3, so we plot that point in orange. There's our center. Now our vertices are going to be adjustments of that point, different directions, but we set a horizontal transverse axis. We can count 1, 2, 3, 4 spots to the right and 1, 2, 3, 4 spots to the left of that center. But if I was writing those coordinate points, it is 4 plus 2, 3, 6, 3, and then 2 minus 4, 3, which is negative 2, 3. That's exactly where we put those coordinate points. Now for the b value, which helps us make our box, it's not a part of the shape at all. We're going to count above and below the center 3 points so that we can make our cute little box. When we have all of the distances we need to travel around, we're going to still make our little box. It's just not going to be centered at the origin anymore. No big deal. We can still take our protractor or our ruler and make nice lines for my asymptotes. But question, what would be the slope of these asymptotes?
To
Rise, how many?
4.
Rise 3.
Over 4.
3, why did I write a 4? 3 over 4. Okay, we know that that part's there. However, we have translated this off the origin. Before this, our equations for the asymptotes were just y equal some fraction times x. That's great, but that means that it is centered at the origin. Where are we centering this line at? 2, 3, which means when we're writing this, we have to write y minus 3 equal to plus or minus 3 over 4 times x minus 2 to indicate that we are centering this line at the same center as our hyperbola.
Miss, why can't we just draw the line and be done?
We can, but if you were going to be asked what is the equation of the asymptote, which you will be asked, you need to know how to write it. So here we go. If we draw our asymptotes in with our rulers, making it nice and neat. Corner to corner too. Yes, it's just that our corner to corner box does not center itself on the origin, but it's still the same process. I feel like the air just kicked on. Did it get colder in here?
Yes.
Thank goodness, it was getting hot.
What?
They were fixing something on the roof, so maybe they were straight up fixing the air. Okay, so here is our asymptotes. We need to plot the foci, and then we'll be ready to graph our hyperbola. But I'll give you a second to catch up. I see everybody with their rulers out still. The coordinates of the foci are actually going to be really nice for this one because we have a nice normal number for C. But we have to adjust it not from the center, but from the actual, sorry, not from the origin, but from the center of a hyperbola. So that means we are going to add and subtract 5 from the x coordinate of both, of the center. Now, since this is an actual number we can evaluate, I do want you to simplify that down. If it was some square root that you couldn't actually give me the number for, you would show the plus or minus. But 2 minus 5 is negative 3. So we're going to have a foci at negative 3, 3. And we're going to have a foci at 2 plus 5, which is 7, 3. But if you plot those points, don't they look real nice? They're along the transverse axis. They are 5 steps away from the center. And once we have that, we take the vertex on each side and draw a bowl or a branch, getting closer and closer to the asymptotes. We double check that our foci made it inside of the hyperbola. Okay, great. That's a number 1 check for you to make sure you put those branches on the right side. How do we feel? It's detailed. Individual pieces are not hard, but are you laughing at my curve? Listen, the ones I graph on my actual paper with a pencil is much better than what I can do with this Apple Pencil. I promise you it looks much nicer when I do this on paper. This looks familiar, yeah? Let's do it. It's so satisfying to watch this go from looking all crazy to be a standard form of a hyperbola. Follow along with me. Here we go. Thank you for trusting me. We're going to organize this by putting all of the x's together, then all of the y's together with our spaces for the magic numbers, which means we're going to write this as 4x squared minus 24x plus something, and then minus 25y squared plus 250y plus something should be equal to 498. What? 489. We have set ourselves up to complete the square.
Wait, it's plus something, plus something.
It's plus, wait, what?
It's plus box and plus something.
Plus box and plus circle.
Yeah.
You got the
Oh, I see what you're telling me. Thank you.
Plus box, plus circle.
Thank you.
Wait. Didn't you get the y wrong? Isn't it 250 not 25?
Yep, it sure is. Thank you.
Miss, you said it right, but you didn't write it right.
Correct. Do what I mean, not what I do.
Not as I
Do what I mean, not what I do. That's not even the saying.
Do what I do.
Do what I say, not what I do.
Oh my gosh. Okay.
This is one of those days.
Listen, we've all been here. Now, if we remember what we did very first last time after we organized the x's and the y's, what did I have to do to start completing the square?
Oh, the B.
I don't have a b yet because,
Oh, no, you take out the GCM.
correct, I need to divide everything here by 4.
This couple.
Okay, yes, so we're dividing everything by 4. So this is going to be 4 times x squared minus 6x plus some number. What would I divide the y's by?
25.
We're going to divide by negative
Oh,
25.
negative 25.
because we want to be able to subtract these things so that it is actually a hyperbola, which means this becomes y squared minus 10y plus circle equal to, and then I'm going to completely write down the rest of it, making sure I multiply the box times the GCF and the circle times the GCF. And I'm running out of space. I'm so sorry. Here we go.
Plus negative 25 circle.
Mm-hmm.
You mean minus 25 circle?
I do know.
Yeah, plus a negative. Yeah, you get it. Okay, now we complete the square. What was the complete the square pattern?
B over 2 squared.
B over 2 squared, which in this case is negative 6 over 2 squared, which is negative 3 squared, which is 9. My magic number in the box is 9. Bless you. This is negative 10 over 2 squared, which is negative 5 squared, which is 25. That's the magic number that goes in the circle. I can't reach that one. Do we follow? From here, this is when it starts to get really, really satisfying because we have a whole lot going on. But because we're completing the square, the x's reduced down to the perfect square of x minus 3 squared. The y's reduced down to negative 25 times y minus 5 squared. And if we do 489 plus 36, which is 4 times 9, plus negative 625, which is 25 plus 25, we end up with negative 100. That's so satisfying. Now, this doesn't look right, though, because what should these equations be equal to?
1.
1. So what do I need to divide everything by?
Negative 100.
Negative 100. Some interesting things happen in this problem when you divide by negative 100. What is 4 divided by negative 100?
25.
Negative 25.
Negative 25. So I'm going to have x minus 3 squared and then negative 25. What is negative 25 divided by negative 100?
4.
Positive 4. Interesting. Hang on with me. And 100 over 1, negative 100 over negative 100 is 1. Now that looks wrong, yeah? We know this is a hyperbola. What should be in the middle of a hyperbola equation? Minus. Don't I have a minus sign?
Yeah.
It's right here.
Oh, you should move it.
So we have to move it around. This hyperbola is actually y minus 5 squared over 4, because that's the positive thing. And then minus x minus 3 squared over 25. The negative term should be second. And because we had to divide by a negative 100, it changed which of the terms was negative. It should go second in the equation. And that's important to nail down because now that I have written it in the correct order, what kind of axis is this going to have? Vertical or horizontal?
Vertical.
Vertical, because the y is in front. I see the confusion. Where did I lose you?
Everywhere.
Oh, when you started the equation.
Like up.
All the way.
Okay, bet.
No, you don't have to read.
Are you sure?
Yeah.
I want you to learn.
I'll consider it.
Okay.
I'm about to go.
Now, we've gotten here. So let's say maybe we need help with completing the square, but once we get to standard form, what should we do to start to graph this hyperbola?
Center.
Yeah, where is the center?
5, 3.
Eh,
No, 3,5.
It's actually 3, 5. Because what's always next to the x term? That's h. K is next to the y. With a hyperbola, they might be out of order.
Yeah.
This is h. This is k. The x has the h. The y has the k. And the problem we did before that, x came first, so it didn't look any different. This time y comes first, so it looks different. Okay, what's the a value here? 2. Very good. Thank you for not saying, wow, get the right color. Miss Quigley, I don't know what's happening here. What's the b value?
5.
5. What's the c value?
Square root of 29.
Square root of 4 plus 25, which, yes, is the square root of 29. And you cannot take the square root of 29 nor break down the number 29 because it is prime. So we leave it like that, which means that we can use this information to find the equations of our asymptotes. I find it easier to start with the graph than try to remember the equations. So if we go to 3, 5, here's my coordinate point for my center. You guys told me this has a vertical transverse axis, so I'm going to go 2 above and 2 below with my blue, and 5 to each side, 1, 2, 3, 4, 5, with my fake minor vertices, 1, 2, 3, 4, 5. Then I can draw my little box. Once you have the little box, you can use your straight edge, your ruler, your protractor, side of a piece of paper when you go home and don't have a ruler, to graph. Yeah, it's a straight edge. You can fold a piece. Yeah, it's still straight.
What is it like?
Okay. So we've got our asymptotes. We know our boundary lines. But we've lost our brains. Oh no. Okay.
No.
The only thing, now wait, we need the equation of these asymptotes. But remember, it comes from the center and then the slope of these diagonal lines. If you start at the center and you get to this corner, what's the rise?
2.
What's the run?
5.
5. So we're going to have an asymptotes with the equation that has y minus 5. I don't know why I put that in parentheses. Let me erase those. Equal to plus or minus that rise over the run multiplied by x minus 3, which again is coming from the center. Last but not least, I want the coordinates of the foci, just to make sure we're plotting this right. Are we going to add square root of 29 to 3 or square root of 29 to 5? 5. So our foci are going to be at 3, 5 minus square root of 29 and 3, 5 plus square root of 29. Which for graphing purposes, this is approximately negative 0.385, and this is approximately 10.385. So we can plot our foci. If we plot those, we stay all on the x-coordinate of 3, going down to a little bit under the x-axis and a little bit over what's off screen. A little bit over. Then you can take your vertice and connect it really widely here to the asymptotes. And voila, we have the hyperbola. I feel like we're doing okay once we get to standard form. I realize with the ellipse double completing a square and the hyperbola double completing a square, that's where we're going to run into some issues. So when you get to those on your homework assignment, slow down, write them down, come ask me for help, ask somebody else for help. Don't give up.
So I'm going to do it all my